In Module 6, we are going to talk about improper integrals. Improper integrals here refers to definite integrations with limits a and b, where either one or both of the limit is taking the values of infinity. The other types of improper integral refer to the situation where at certain values of x within the range of integration, the function fx at these points are not well defined. Both are considered as improper integral. The first example of the improper integral we will see is to evaluate the area of the function y equals to ln x over x squared for x ranging from 1 to infinity. The area is calculated as the integrations of the function y by taking the upper limit to infinity. If the limit of the integrations in terms of b is finite when b is taken to infinity, then the limit of the function that represents this proper integration would be the value of the area under the curve considered. The integration for the area under the curve for y has to be carried out in two steps. The first step is to obtain the explicit expression of the function in terms of b that represents the proper integration of ln x over x squared between the limit of 1 to b. At this stage, b is assumed to be an finite number. In the second stage, we will then take the limit b to infinity for the expression of fb, where fb is a function of b defined as the proper integrations for ln x over x squared evaluated between the lower limit of 1 to b. Therefore, the first stage is just an integration procedure. The second stage is a limit taking procedure. So let's see how we are going to evaluate this improper integral in the following. In step number 1, we would define a function called f in terms of a variable b, where the b is replacing the upper limit of infinity in the original integrations, while the lower limit remains the same value of 1. So we recognize that here f of b is an integral function where the variable is the values of the upper limit. It is assumed at this stage the values of b is an finite number. Once we have obtained the expression for f of b, the second step is then to perform the limit taking procedure of the function f by setting b to infinity. So let us proceed with step number 1. To obtain the expression of fb, we look at the indefinite integrations of ln x over x squared. This integration could be carried out by using integration by parts or by referring to the integral table, which we have already discussed in module number 5. Here, we would want to perform the integration by referring to the integral table. If you refer to the integral table and look for the items that involve exponential and logarithmic function, item 117, you find this item x raised to the power of n times ln ax raised to the power of m. And the result of the integration is given by here with the condition that n is not minus 1. In the present case, we are integrating the function of x minus square ln x. So it is obvious that here n is taking the values of minus 2, m is taking the values of 1, while a is taking the values of 1 as well. So I will write down the results of the integration for item 117 to the right hand side of the integration we are performing. Here, I would write down n equals to minus 2, m as 1, a is 1. So the term x to the power of n plus 1 would then be x to the power of minus 1, because n plus 1 is minus 1. So this term translates into ln x raised to the power of m, which is 1, divided by n plus 1, which is minus 1. I have minus m over n plus 1, which is 1 over minus 1, times the integrations of x to the power of n, which is minus 2 times log of x raised to the power of n minus 1, which is just 0. So here I have completed writing down the results provided by the integral table. And let me tidy up my expressions. The first term here would be simply minus ln x over x, while this term of ln x raised to the power of 0 refers to 1. So the whole term is simply plus x to the power of minus 2 dx. This could be simplified further to be minus ln x over x minus 1 over x plus n constant. That is the integrations of ln x over x squared dx. With the results of this indefinite integration obtained, we can then form the expression of f of b. F of b is simply equals to the definite integration evaluated between 1 and b, which can be expressed in this form, which is the result of the indefinite integration to be evaluated between 1 and b. So this could be worked out quite straightforwardly as ln b over b minus 1 over b. These two terms are obtained by substituting b into the x of the square bracket. Then we have another term which is the values obtained by substituting x in the square bracket by the values of 1. And that would be just equals to minus 1 over 1, where the term involving ln1 is 0. So we simplify this a little bit. It will be ln b over b minus 1 over b plus 1. So that is the expression of the function capital F in terms of b. So that completes the first step. The second steps involve the limit taking process of b going to infinity for the function f of b. And this is just written as the limit of b going to infinity for ln b over b minus 1 over b plus 1. And in this process, the term 1 over b goes to 0. So we just drop the term 1 over b, and this term will remain as a constant of 1 irrespective of the values of b. So we will have 1 that comes from this term, and there will be no term contributed from 1 over b. Then we have the limit of b goes to infinity for the function ln b over b. The limit of ln b over b could be easily obtained by using L'Hopital rule. L'Hopital rule says that since both log b and b goes to infinity when b goes to infinity, so this is in an indefinite form of infinity divided by infinity. Therefore, we can apply the L'Hopital rule to equate the limit of ln b over b with the limit of the differentiations of the ln b with respect to b divided by the differentiation of b with respect to b. So that would end up to be limit of b goes to infinity. d db of ln b give me 1 over b, while d db of b just give me a value of 1. So that amounts to taking the limit of 1 over b, and it is simply equals to 0. The limit of ln b over b is 0 when b is taken to infinity. So we come to the conclusion that this term, the limit of b goes to infinity, is 0. Therefore, we end up the values of the f of b is 1 in the limit b goes to infinity. The results for the integrations of the area under the curve is simply equals to 1. So that is the solution to the improper integration of the first type for example 30. In conclusion, we have discussed how to perform the improper integral on example 30 to find the area under the curve for the function y equals to ln x over x squared from x equals to 1 to infinity. The area under the curve is obtained by performing a two-step procedure. The first step is to obtain the expressions of n definite integrals in terms of b, and the second step is to take the limit of the resultant integrations in terms of b to infinity. Here we first obtain the indefinite integrations of ln x over x squared by referring to item 117 in the integral table. so that we can obtain the expressions of the integral function f of b in the form of ln b over b and 1 over b. Then in the second steps, we take the limit of the function f by setting b to infinity. By applying L'Hopital rules, the limit of ln b over b is shown to be 0. So it's a term 1 over b is 0. Therefore, we end up the limit of the function f of b is 1 when b tends to infinity. And this limit is the values of the area under the curve for the function ln x over x squared between 1 and infinity.